I used to upgrade my PC every 4 years or so, and every time I upgraded, the new one was about twice as fast as the old one when I tested it. But now I'm wondering, how much faster have PCs gotten at executing really old-style workloads over the years? And I'm talking old-fashioned C code, single-threaded, not even using floating point. And I have 8 old PCs of various ages, including this one here, which was my daily driver till 2012, and it still runs Windows XP. And I just got a new one, which is my fastest yet. This one's provided by Geekom, who are sponsoring this video. More on that later. And back in 2002, I wrote a C program to find all possible arrangements of the 12 Pentomino pieces in a 6x10 grid like this, and I figured that would be a really good benchmark. And if I only counted the solutions found instead of printing them out, I was able to get that down to 90 seconds on my 500 MHz Celeron at the time. But I no longer have any computers that old, so I'm not going to go that far back with my tests. And to make this properly old school, I'm compiling my code on Windows XP with a Microsoft C compiler from 1998. And my old XP box could run that in just over 7 seconds. My present daily driver can run it in half of that time, but my newest computer, this one, actually takes longest, almost as long as the old XP box. So now it starts to get interesting. Why so little change over more than a decade, and why is my newest computer slower? The thing is, my old school program actually uses unaligned access of 32-bit words to process 4 bytes at a time, and the Intel i9 in this newest PC doesn't like that so much. And that unaligned access optimization is definitely an old school trick. But that same year in 2002, I also wrote a 3D Pentomino solver, and that one has a lot more pieces because it also includes the non-flat pentominos. And that program doesn't use that unaligned trick, so it's perhaps a more fair benchmark. And for that one, I'm just timing how long it takes to find the first solution because there's so many more solutions, and we can see the time goes down and then it goes up. Now, to be fair to Geekom, who provided this computer, I'm compiling 23-year-old code with a 27-year-old compiler on a 17-year-old PC. But it's nicer if the bars get longer as the speed gets higher, so this is scaled 1 over time relative to my 2010 Core i5 PC, so that one there is a 1, and my current daily driver is about 1.5 times faster than that, and the Core i7 is actually slower. Now, both of my Pentomino solvers actually implement this sort of heuristic, which is try this piece, try that piece, try the other piece. So they don't really go in a straight line, lots of branching in unpredictable ways, but newer processors with their long pipelines really perform well if the code sort of goes in a straight line predictably, so this benchmark doesn't favor newer computers. To run the clock much faster on newer processors, they do much less work in one clock cycle, and that means breaking the instructions into phases that are very, very small, so a new processor will have at least 10 instructions on the go at any one time, but if it needs to change the code path, all that stuff needs to be discarded and restarted. So newer processors do a really good job of predicting which way a branch is going to go so that it doesn't have to discard stuff. And I thought about this problem back in 2005, so I implemented a bitwise CRC algorithm, and depending on what bit gets shifted out, it goes one branch or another. So that causes unpredictable branches because that's pretty random what comes out. I also implemented this same algorithm but using an expression instead of an if statement. And back then on my Pentium 4, the branchless version, which is actually more complicated, ran twice as fast. So I thought, hey, that'd be an interesting to test too. But a much more sensible way of calculating that CRC is with a table-based approach, so I'm testing that too. And running that on a lot of data, here's my times. Green is table-based, the fastest of course. Next is the non-branching version, and the slowest is the branching version across all my computers. And then scaling all those numbers relative to my 2010 i5, at least now the bars are the same height, and we see the performance goes up, but we haven't even doubled in 13 years. And I know that was actually 15 years ago, not 13 years ago, but I'm going by processor release date, and the i9 in my new PC was actually released in 2023. And putting all 5 tests together, scaled to the 2010 i5, we see the new PC is winning, just not with the Pentominos. So I decided to take a 24-year leap forward in compiler technology, so now using the Microsoft Visual Studio compiler from 2022. And here's my execution times, and they definitely go down, and the new PC is now definitely winning. And here's the relative speed up using a new compiler versus the old compiler, and we can see the if-based CRC, that's the bars in orange, have gotten almost 5 times faster with 2 of these computers, and about 4 times faster with the newest computer. And the reason my if-else based CRC code is so much faster with a newer compiler is because in 1995, Intel introduced a conditional move instruction for the Pentium Pro, but my compiler from 1998 couldn't use that yet because most of the computers out there at the time were older. So the new compiler now doesn't need to worry about whether that code is going to run on a Pentium 1 or 486 or even 386, so it can use that instruction and with that avoid the conditional branch, which doesn't screw up the pipeline and makes execution that much faster. But my goal was to screw up the pipeline, and I added this one line here to count how many times I was not shifting into polynomial. And that got Visual Studio to use the branch again. And I call that one CRC if count, and it's the bars in red, and it basically takes about twice as much time as without that count. And looking at relative speed up again, new compiler versus old compiler, the bars in red are not out of line, not like the bars in orange. And again, scaling the performance relative to my 2010 i5, the 2023 i9 is now more than double the performance. And now relative to the old code with the old compiler on the 2010 PCs, the performance increase is better. So for instance, my Pentomino solver is now almost 4 times faster. Now that's running on the performance cores of the i9, but the i9, like a lot of new processors, has 2 types of cores, performance cores and much more efficient efficiency cores. But the efficiency cores also run slower. And so I added the efficiency cores next to the performance cores on this chart, and you can see they're less than half as fast, and we have to go back to my 2010 i5 to get about the same performance. But these slower efficiency cores are nice too because it means this thing can run more efficiently when it's not super busy. So looking at my power meter, right now that PC is drawing 5 watts. And that means it stays nice and cool. Most of the time its cooling fan isn't even running, and that cooling fan is actually quite quiet, quieter than this one is when it's idling. And I really like a quiet PC, so this will be my new daily driver, especially because it outperforms my bigger PC right behind the monitor. And popping the lid off of this one, I can tell there's a centrifugal fan in there, sort of like this one, and it blows air out through some cooling fins on the back. Sort of like laptop computer fans these days, except this one is bigger. I was afraid that it might use some tiny little fans like this one, because those things are just noisy as heck, but this makes a nice and low sounding whoosh when it runs. And this small form factor PC from 2008 is actually my loudest PC because it uses a bunch of tiny fans. And that sound is so annoying that every time I've run a test, I've been turning it off straight afterwards. And it just opened up on the bottom. Here's the NVMe drive, 32 gigs of RAM, and another short NVMe slot. Very nice. Plus on here, I've got a drive bay, and I can take an old-fashioned laptop drive in here. Very nice. And I can even stick a spinning platter drive in here. But to do that, I had to take out these little rubber standoffs, which are there to keep the thinner SSDs from rattling around. But I won't be putting a spinning platter hard drive in that thing because those make noise. Now, do you remember Moore's Law? I mean, performance was supposed to double every 18 months or maybe every 2 years, and back in the 1990s that was actually true. But here, I'm seeing a performance doubling over 13 years? Of course, I'm testing with an old school load, which is for a single core like computers had back in the 1990s. My oldest computer I still have has 2 cores. This thing has 14 cores. So that's a huge performance boost if your code can use all these cores. My Pentomino heuristic does not. So I benchmarked how fast all of my PCs could recompress video with FFmpeg, although that's excluding my Windows XP PC because it won't run the latest version of FFmpeg. And scaling everything to my 2010 i5, the 2007 PC is dramatically slower, and the newest one is about 5.5 times faster, although not hugely faster than the Core i7, that's my normal editing PC so far. And the jump from this one to this one is fairly small because this one is effectively like a laptop folded into a small box, and it uses a mobile i9, which is not the speed demon that the desktop one would be. And if we look on here, I used a quad-core i7 laptop. That's this one here. It was actually a gaming PC at the time, but it's still slower than my desktop that was 3 years older. And again, I'm using 2023 for the date on here because the processor in here was released in December of 2023, but it is a brand new PC. And looking at the speed increase, ignoring this one because it's a mobile processor, so this is a desktop and my 2010 is a desktop. We got 9 years between them, a 5.2 times increase in performance. That works out to an annual increase of 20%, or about 3.78 years per performance doubling. So that's roughly 4 years per doubling, which, is twice what it was in the 90s, but is better than I thought it was. The thing is, right around 2010, it got much harder to get more single-core performance. So what chip makers have been doing since then is adding more cores. You can't get a single-core PC anymore. And adding more instructions that are good for things like video or 3D or video games. So as long as your software is able to use the newer stuff that newer computers have, there's still performance increases to be had. It's just for old school workloads, they don't really get much faster anymore. Now thinking about my CRC tests some more, the table-based one is of course the fastest and it doesn't trip up the CPU with branches, but it still doesn't make optimal use of modern processors. That implementation just keeps running this line of code over and over again, but this expression here is dependent on the output of this expression, which means the processor cannot start evaluating the next loop iteration until the previous one is done and has a CRC. So what if in that same loop I evaluated 2 separate CRCs at the same time? So now I'm passing in 2 sets of data to evaluate the CRC on, and I alternately do one and then do the other. And to my surprise, that loop ran at exactly the same speed, even though it was doing twice as much work per iteration. So I started evaluating more and more CRCs at the same time, and I got up to 6 before I got significantly slower. So instead of having all these copies of the code, I then just switched to a loop so that I can specify how many CRCs I want to evaluate at the same time. And testing this on my old PCs, even my oldest 2007 PC, going from 1 simultaneous to 2 simultaneous doesn't increase the time very much. Only when we get past 3 does it kind of increase roughly linearly. And then the Geekom with the i9 actually takes the longest to pick up, so the time is almost constant until we get to 6, and only then does it start to go up. And now scaling that to relative to my 2010 i5, so that one is now always 1, the new i9 is at 3 times the performance, whereas before I was only getting twice. And next I normalized it to what the performance is at many iterations, so making sure those ones settle at the same level. The i9 takes the longest to reach its full potential, up to 6 simultaneous, whereas my other computers, by the time they're at 3, they're pretty close to having reached their full speed, and by 5, they're there. So that tells me the instruction pipeline of the new i9 is long enough that it can work on 6 iterations of the inner loop at the same time, whereas with the older processors, it's maybe 3 or 4 at the same time. And this data dependency can be a problem, just totaling things up. So here I've got a little test program, computes the sum of squares, but of course the total needs to be added to itself. So I thought, what if I add the odds and evens separately, just looping by 2, doing the odds and evens and summing those later, and why stop at 2? So then I'm also doing it by 4 sums and adding those later, and running that on my i9, that's the Geekom PC. I get some gain here going to 2, but then going to 4, the gain is almost minimal. But then testing on my other machines, my 2019 i7, it doubled going to 2, and then a very small gain to 4. This 2015 laptop, again, the speed doubled, but going to 4, almost nothing. And then older computers, my 2012 i4 had a very small amount of gain. Going back to the 2010, almost no gain, and 2007, it actually got slower, doing more than 1. So that was kind of interesting. This sort of data dependency optimization is one I hadn't thought of before, but it only works on computers that are newer than 12 years old. It's that, unpredictable branches, and cache misses that really dominate performance, although I'm not at all getting into cache misses in this video. Now, all this was done with Intel processors, which we know are no longer the fastest processor, although looking things up for single-threaded performance, Intel might actually still be in the lead. But the Apple M series, that's a different story. Now, I don't have any Macs myself, but my friend Jeff Gerling does, and I got him to run some of these benchmarks and add them to the table. And this is an M2 Air, and this is an M4 Studio. And again, all scaled compared to my 2010 i5 PC. And at the table-based CRC benchmark, the M2 is actually slower than my 2010 Intel PC. The M4 is a little bit faster. The other CRCs, they're about the same, but where the M series really shines is with the Pentomino benchmarks, which are actually a much more relevant metric. So the M4 Studio is about 1.7 times faster than my i9, but it's also a bit newer. And for the multi-CRC, the times jump around a bit with the M series, so doing 8 at the same time, it does fairly well, and that's true for both the M4 and the M2 running over multiple tests. And I've read about Intel processors that the performance can be a little bit unpredictable because some things just trip them up, and it looks like the M2 and the M4 are even more inconsistent that way. And looking at the graph scale to my 2010 PC, they're mostly ahead of my i9, that's the green line here, although not for some iterations, and not hugely ahead, maybe 1/3 ahead on average. And scaling the relative performance to what they settle at, the M2 and M1 don't really settle at anything until they get to 9. 8 is the sweet spot, and before that they do relatively poorly again. And given the relatively erratic nature of the performance of the M series chips based on how many CRCs I do at the same time, it's a bit of a cautionary tale about optimizing for them. But that said, the M series chips are by and large considerably faster than the i9. But I don't like Macs very much, so back to the sponsor of this video, Geekom. So this one has got 2 USB ports on the front, and then 2 more on the back right here, and 2 USB-C ports, one here and one here, and 2 full HDMI ports and an Ethernet port. And the USB-C ports can also do video, so I'll just plug this in here. And this is not a laptop computer, it's a monitor and keyboard dressed up as a laptop. And I can fully control it even with an external mouse plugged into this just over the USB-C, because this has got video plus the regular USB. So with the USB-C ports also acting as video output, it can take up to 4 monitors, although the built-in graphic is just the regular Intel graphics, so it's not a gaming PC. And with a USB-C providing video out, you could buy a USB hub and basically plug everything into that, and then be able to take the PC home and to the office back and forth and dock it just by plugging in one USB-C. Plus power, of course. And with just 4 USB ports on the back, plus 2 on the front that I don't like plugging in all the time, it is kind of limiting, so I've already got the hub plugged into this one. And I just tried my benchmarks under Windows System for Linux using GCC, and it's about 10% faster. So this is the Geekom i9. Here it is under Windows Systems for Linux, and the Pentomino ones are about 10% faster. The Mac M2 Air still beats it, and the M4 beats it by more, but the margin to the M2 has gotten fairly small. And I also tried the GNU C compiler on Windows, and I got similar performance gains as running it under Windows Systems for Linux. So the GNU C compiler is a bit better performance-wise, but the Mac Mini still beats this. And the base model Mac Mini is actually a little bit less than this one, but this comes with 32 gigs of RAM and 1 terabyte of SSD, and if you try to get that on a Mac Mini, that's going to cost you a lot more. Plus, you can upgrade the RAM in this thing, and you can stick up to 3 SSDs in there, so a lot better than the Mac Mini. And I uploaded my little performance benchmarks and spreadsheets onto GitHub if you want to look at them. And Geekom has sent me a lot more marketing material and links, which I'm not going to cover individually here directly because I think I've been plugging that PC pretty hard already, but there's purchase links in the description. And it's kind of necessary to mention the Intel performance libraries, because if I don't, everybody will tell me about them. So, of course, you'll get more performance if you use the Intel performance libraries, because they can take full advantage of the SIMD instructions of the processors. But that's if you're pulling in that library, which of course won't work on ARM, for example. And also, what if your algorithm is something that the performance library doesn't handle? So if sometimes you can double your performance just by tweaking data dependencies, that can be a very useful optimization without pulling in a lot of extra stuff.